right, our last presentation of the day, Mark Johnson presenting instruction set support for detecting injection exploits.
Hello, everybody. Thank you for being here. I appreciate that it's the last time slot of the day, so thank you all for sticking around. My name is Mark Johnson. I'm a research engineer here in the Intelligent Systems Division of Southwest Research Institute, and this presentation goes over a research project that I ran a little while back where we added some custom instructions to a RISC-V soft CPU with the intent to mitigate code injection vulnerabilities. So we'll start off with some general background information about various existing secure processor architecture efforts and about code injection in general for those with less of a security background. We'll talk a little bit about the specific idea that we had that we thought could help, how we effectively implemented that, tried it out, and of course what we learned. So starting off with the background, security of course is becoming a much bigger concern in the space sector. We're seeing proposals and projects with new cybersecurity requirements like secure boot and things of that nature. At the same time, sort of seems tangential at first, but it'll be a recurring theme here. RISC-V, of course, is rising in popularity. There was a previous presentation, a couple before mine, that even mentioned RISC-V soft CPU, so clearly relevant. And RISC-V, one of the reasons it's a convenient choice is there are many soft processor cores available. There's lots of options. And one thing that's very interesting about deploying those soft processors is that they're not static components. They can be modified to do interesting things. You're not stuck with the capabilities that are included on the chip that you buy. Some interesting examples of secure architectures that have been developed are SwRI, which I have some personal experience with, and it uses capabilities, another security-specific concept, but in essence, it prevents all sorts of memory access errors. So things like array overruns, out-of-bounds accesses, things like that are prevented by capabilities in SwRI. The other two we're a little less familiar with, but they serve as good examples of the kind of principles that are being looked at by current researchers. So Sanctum providing provable process isolation, and if I'm not mistaken, that's provable in a mathematical sense. And Ascend, which has the aim of encrypting or obfuscating the computation such that I believe if you had access to the board, you somehow fly up into space, grab the board, probe at it with an oscilloscope, you can't tell what's going on. So these aren't flight-rated examples, to be clear. These are just examples of secure architecture efforts. So the problem with those secure architecture efforts, code injection. So if you all read XKCD, you'll be familiar with this comic, the classic Little Bobby tables, where an unassuming school administrator presumably entered this kid's name and dropped the student's table. So this is a class of vulnerabilities, effectively, where an attacker gets to craft a payload, send it to your system, and get it to run their code. It's a mechanism for arbitrary code execution, which I think is often considered the sort of holy grail of exploits. When you can run your code on someone else's machine, that's a lot of power. So how this relates to space, if we hypothetically ever have a CCSDS telecommand payload that ever gets used in some kind of a system command or some kind of an interpreted environment, that's immediately a potential danger, a potential opportunity for those attackers to gain access. And these secure architecture efforts that I discussed previously don't offer any sort of protection against this. Their focuses tend to be on problem domains that are maybe slightly more well-defined, that have maybe more clear-cut solutions. So as for solutions to code injection, the obvious one is input sanitization. It's even called out in the XKCD comic from a few slides ago. This is a sort of careful manual process where you're checking that the inputs that come in are safe. It can involve modifications to code bases that are fairly large. Depending on how it's implemented, it could be fairly expensive if your inputs are really huge, for instance. The main thing that concerns us about this is that the process is error-prone. It relies on your developers to recognize the opportunity for these vulnerabilities and to think ahead and proactively attempt to deal with those. So as we're doing this secure processor research here and interacting with some of these secure architectures, the idea that struck us was, what if our soft processors could also do some of the heavy lifting in this regard? So on to our approach. So the idea that we had is actually a very simple one. It's a module that keeps track of where those input values are in memory. So it's kind of like a dedicated MMU, but it's keeping track of memory that contains data that maybe we don't trust. And we thought a little bit about whether or not compilers could possibly support this as a feature, but there seems to be more nuance to the problem in that there is a way that the system is expected to execute. There's a set of things that it is supposed to do that are maybe not entirely captured at that level by the compiler. So it's a difficult problem. And we'll go over this a little bit in future slides, but our idea was also to try to interface this with those custom instructions so that the places where that data comes in can mark it as being unsafe, and the places where it's being interpreted can see if it is or not. And if not, of course, there's any number of ways you could try to remediate that. So a little bit more about why as a custom instruction. For one thing, it's just an interesting way to do it. There are some benefits that we think exist, like the interface being very low latency. We're not running accesses over a peripheral bus that maybe has a ton of other stuff connected to it. It's one other interesting facet is that because it's a module integrated into the processor, it's not running in the software and left to the whims of whatever processes are manipulating it necessarily. So if you're running a Linux-based operating system and you have virtual memory or you have shared memory between processes where maybe the same data is accessible through different references to different processes, integrating it this deep into the stack allows it to go off of the physical memory and not be fooled by those. But my favorite reason is that this makes the software really easy to write. This code here, I apologize if it's not very readable, but this is the whole software driver, and I put driver in quotation marks because really all it is encoding some of those instructions with the custom instruction opcode. So now to compare the two approaches in a little more detail, the sanitization approach requires you to effectively add some code along that telecommand control path or along that data path where the payloads are going that is, in the best case scenario, you can just check to see if the payload contains bytes you don't like. You can say that has a quotation mark in it, it has a semicolon, I don't trust that. That approach can work in many cases, although it might lack precision or it might not be applicable to all of your fields of input. You may have to kind of duplicate code that looks like that across the different contexts, and that's sort of what the third bullet tries to hit on there. And a more complicated way to do it would be to, for instance, right before you interpret whatever it is you're interpreting, try to reparse that command and make sure that it's structured the right way. But of course, that's difficult to do as well. So the most likely outcome is that you're going to have some kind of arbitrary criteria that you're worried about, depending on the context of how that data is eventually going to be interpreted. So where we see a custom extension kind of fitting in is this diagram here on the right shows the sort of elements of the idea in orange there and the existing parts of the system kind of in blue. The idea is once you have the data in, that data may come in one place, and the data, or well, the code that ingests that data can mark it as untrusted. That's hopefully, you know, only a one line of code diff to your actual source code, and that might be in your libraries or in your drivers. And I guess also wherever that data gets copied, if you have string copying functions, you can have it do, you know, if this data is not safe, then mark the destination as unsafe also. but these are minor modifications. And of course, beyond that point where it gets interpreted, you can add another short piece of code that simply refers into that module and says, is the thing I'm about to do, am I about to do this because of data that we trust or data that we don't trust? And we think if you place that check well enough, that could also be a very simple diff to your source code. And one thing that's particularly interesting about this approach is the places where these source code changes happen don't necessarily have to be in the actual application code that is relying on that sort of interpreted component. The box on the far bottom left there does not have any source changes. And that's a useful property of this approach as well. So how did we actually try this out? First, we had to have an algorithm, and this slide is complicated, and for that I apologize. But what we ended up with was a sort of parallelized binary search-based algorithm where we have a list of records that represent regions that aren't safe. We can do we can do in the hardware 2 simultaneous binary search processes to figure out where the start and end of a lookup range fall with respect to any of the ranges that currently exist in the data. So this binary search-based approach scales really well with the number of regions that you may be concerned about. And it's parallelizable, which is convenient. This does, of course, imply certain properties about the data. So the binary search aspect means that, of course, it has to be sorted. So this makes the insertions more expensive when you add new regions of untrusted data to the records. That is an expensive operation. And in the diagram on the right, these red boxes illustrate how those lookups can overlap with any existing entries. And the arrows show sort of how much shifting down all of the other entries need to be in order to sort of make the data well-formed again. However, of course, the insertion, while it is expensive, is going to be infrequent. This is going to be contingent generally on I/O operations, which are much slower. So as long as the lookups are very fast and the insertions are not too slow, then the exact cost of the insertion is not really a major concern. All right, and once we have the algorithm, we have to implement it. So for prototyping in this project, we actually landed on trying to use Vitis HLS for this because we were targeting a Xilinx board and it looked like a convenient option. The ability to get fast resource and latency estimates meant that we had a fast design turnaround that made the engineering time pretty quick. And we found that to be useful. So that's, I suppose, one of the lessons learned. Another interesting point is that before developing the hardware, we had a basic software model of how the module should behave. And that was written in C. And given that in Vitis HLS, most of the source code is in C, we can link that existing software prototype directly into the test bench to generate the golden outputs. And that makes the test bench writing very easy. And of course, working at that high of a level also offers a high level reconfigurability. So targeting different frequencies, the HLS will try to schedule the operations to facilitate the target frequencies. And we have the actual post-synthesis estimates here in the figures. So the search loop there taking between 2 and 10 cycles. It's very fast. And the utilization percentage being well under 10%, we were quite happy with. And once the thing is implemented, we have to put it into a processor somehow. So this is where RISC-V comes back into play here. RISC-V is especially convenient, partially because there are lots of open source, permissively licensed options to play around with, but also because the RISC-V specification itself prescribes specific opcodes for custom instructions. And that, of course, makes it very straightforward to not mess with what's there too much. So these are the 2 that we eventually landed on for our efforts. Pico RB32 being a very small design, and we chose this one because of its coprocessor interface, which made integration very straightforward. So the second of the 2 that we performed integration with was Black Parrot, which is a bigger design, more powerful. It can run Linux. But of course, that makes the integration more challenging because of the complexity. So although both were selected, the Pico RB32 integration is further along, so that's what I'll be focusing on for the remainder of the presentation. And here's how that integration went. So this diagram looks very complicated, but it's actually a pretty simple process. This diagram pulls out every little detail of things that we added or changed in order to perform that integration. So this diagram is kind of more for our own documentation's sake, but it's a useful visual to highlight the different areas of change. This is the hard one. Updating the processor to recognize that new opcode is challenging because you have an existing design that you may have to modify if you don't have that coprocessor interface. One useful pattern we discovered, though, between these two integration efforts was that you can use some existing instructions, especially very computationally expensive instructions like integer division, to get hints as to how to integrate things, because very expensive instructions tend to need to stall pipelines and things, and if you don't know how long your module needs to run necessarily, or if it takes longer than an instruction with a fixed latency, then it may be helpful to know how to do that stalling of the pipeline to wait for the module to be done with its calculation. So, and as an interesting note, both of the processors, we did go with that strategy. So Pico RB32 actually uses that coprocessor interface for a discrete integer division and integer multiplier module. So the way that we hook up our own module to that interface, very similar. And in Black Parrot, integer division falls under this long pipeline that's able to stall the processor for a while. And so it turned out to be a useful approach there. So a useful pattern, a useful way to get some hints out of what's already there. Once that's done, the rest is honestly trivial. So implementing the subroutines with the custom instructions, that was, the full source code for that was on that slide that I showed. So not a very difficult task. And then once you have those exported for linkage, you can declare them extern and simply call them from the high-level code. So it's very straightforward once that initial hurdle is crossed. On to the results. So in its default configuration, the design handles up to 64K, or I guess it's really 65K, non-overlapping regions. And of course, if there are regions that do overlap, they get merged automatically as part of the insertion process. Again, in its default configuration, the lookup latency actually lands between 5 and 10 cycles at an estimated maximum operating frequency of 142 megahertz. And that was with a 100 megahertz target frequency. So if we needed to run it faster or slower, again, that's one place where the HLS component is useful. We do have a basic proof of concept demo and also a randomized test process here shown below in a modified version of Pico RB32's test firmware. The right next to where it says checking ranges, the pluses and minuses indicate whether the test range was in the set or not in the set of data which the module considers not safe. And that's mostly for visualization purposes to make sure that the pseudo-random numbers really are pseudo-random enough. And the pass there at the bottom indicates, of course, that everything was successful. So what did we learn from this? Adding new instructions to a soft processor is surprisingly practical. And there are interesting things you can do that are security related or even not security related. And this process demonstrated some interesting engineering trade-offs for us, especially in terms of the simplicity of the software and in various other regards. And of course, useful to note that the expensive operations can be useful hints as to how to do that. The actual module itself and the underlying algorithm also probably have other applications. So in this case, we're applying it as a security tool for a RISC-V based soft CPU system. But really all that module is doing is keeping track of regions of memory that have a certain property. And so this is obviously a fairly generic tool that could be used for lots of other things. PII was brought up in a previous presentation, for instance. You could use it to keep track of that. And it also isn't the idea isn't restricted to RISC-V either. So RISC-V was convenient because it has, in its specification, clearly delineated opcodes for custom behaviors. But there's nothing stopping you from trying to do the same thing with a different processor that you have permission to modify. And of course, the last takeaway, HLS tools were surprisingly useful for us to prototype these components. We could have developed everything in Verilog. Would it have been smaller and faster? Probably so. But this was not a very long project, and that was a risk of running out of time just trying to develop the algorithm to make it good enough. So that faster design turnaround time turned out to be a useful lesson for us to take when prototyping future hardware components. And if the resulting RTL that you get from the tool is reasonably well optimized, good enough for your purposes, then you just might be willing to stick with it. Some opportunities for future work. Trying to smartly remove tracked regions when they're no longer unsafe is not something we really were all that concerned about, was not really in scope. But for instance, if you're zeroing it out with memset, that's an easy opportunity to just remove that from the list. Deeper integration with the architecture also would be another interesting direction to take this. So we're sort of relying on hooks into functions a little bit in our case, but there would be a way, in theory, with a better insertion algorithm, that you could transfer that unsafe status of that data through loads and stores to and from registers. And then the last little bullet down there, requiring an elevated privilege level would be another interesting way to take this, so that software that is misbehaving already, for instance, can't simply accidentally clear the entire table and open it up for vulnerabilities. So anyway, that's all I have. Thank you all very much. If there's time, I'll be happy to take questions.
Yeah, I got one. Does VT's HLS work for space FPGAs too?
So in that case, it depends on whether the target is a Xilinx chip or not, because the Vitis HLS tools only support Xilinx products, although I know Microchip has their own HLS solution that I am not as familiar with.
I have one more. Is there any interest in augmenting RISC-V to support this new instruction down the line?
So this ties back into previous slide. Maybe, yes. So what we think is that probably there is no way to have the compiler support this, because it sort of relies on the developer's intent behind whether the system is going to behave correctly or not based on its input data. So it's not a very easy thing for the compiler to infer based on your code what your code is supposed to do. Because if it could, there would also be no such thing as a logic error.
I think that's it for the questions.
Yep.
Thank you so much.
Thank you all very much.